Hey everyone, this is Dr. Walker. This is video 253, torque and magnetic moment. We've already talked about torque, but we want to introduce a concept called magnetic moment that will help make our discussion of torque just a little bit easier. So let's talk about magnetic moment. So the magnetic moment is a measure of how much torque a current loop will feel in a magnetic field. So will it experience a lot of torque? Will it experience a little bit of torque? It depends on the magnetic moment of that loop. The magnetic moment is defined as NIA. N is the number of loops, I is the current in that loop, and A is the area of that loop. So this might seem like an arbitrary definition, but we'll see how it applies very soon. Another thing to know about the magnetic moment is that it is a vector, so it has a direction, and that direction is perpendicular to the plane of the loop. And we'll learn exactly how to find its direction in just a minute. What you can see in this picture here is that if you do use your right hand and you loop your fingers in the direction of the current, in this case the direction of the current would be counterclockwise if viewed from above. So if I view my hand from above, my fingers are going counterclockwise, then the thumb is up. So that upward direction of the thumb is the direction of the magnetic moment that is perpendicular to the loop. Now that we have defined the magnetic moment, we can redefine torque. In the previous video, we defined it as torque equals NIAB sine theta. Well, now we are replacing NIA with mu, the magnetic moment. So now the definition becomes mu b sine theta. So this may sound a little bit arbitrary. What's the point? Well, now it makes it easier to understand this theta, because before, the angle theta was the angle from the normal of the loop and B, right? The angle between the normal of the loop and B. And that was kind of weird because you often think of the angle as being from the loop to B. But now that we have rewritten it as mu b sine theta, then we know there's no question about it that theta must be the angle between mu and B, because those are the only two variables there. So it definitely makes it easier to remember what that angle is. And there's also another reason for defining this magnetic moment. And this reason is because it helps us know exactly which way our loop is going to rotate when it's placed within that magnetic field. The trick to remember is the torque tends to align the magnetic moment with the magnetic field. So that sentence there will tell you exactly which way the loop is going to rotate. In the first picture here, we have the current going counterclockwise as viewed from above the loop. So view your fingers from above, they go counterclockwise, the thumb is up, the magnetic moment is up. That's the yellow arrow, is the magnetic moment. The magnetic moment will want to align with the external field, which is going to the right. That means that the loop is going to want to rotate clockwise so that mu lines up with B, as we can see in the picture on the right. So if you are in this first case here and you don't know, well, which way is it going to rotate? Now you know mu wants to be in the same direction as B. Another thing I want to note is with this definition here, torque is mu b sine theta. You can see that torque is a maximum. You know that when sine of theta is 1, and sine of theta is 1 when theta equals 90 degrees. So that's this first case here. Theta is 90 degrees. The angle between mu and B is 90. That's the maximum torque. It's really going to want to rotate and align with B. However, torque is equal to 0 when sine of theta is 0. Sine of theta is 0 when theta equals 0 degrees. That's this picture on the right. When the angle between mu and B is 0, when they're already parallel to each other, then the theta is 0, sine of theta is 0, there's no torque. Right? It doesn't want to rotate anymore because it's already aligned with B. So that's really useful to know, and it's going to help us with the problems. Let's do a couple of examples. First of all, when is the torque on a current loop in an external field a maximum? So we just talked about this, so read through the answer choices and choose your best guess. Let's go ahead and write down the equation. Torque is mu b sine theta. When theta is 0, no. When theta is 0, sine theta is 0, torque is 0, so that's no. When the loop is at rest, well, that doesn't make any sense because, I mean, it could start at rest, but the torque is going to make it rotate, so the motion of the loop doesn't really affect the torque. So then we have when the magnetic moment is parallel to the magnetic field, or when the magnetic moment is perpendicular to the magnetic field. So we just saw this in the previous picture. When the magnetic moment was perpendicular to that magnetic field, when the angle was 90 degrees, then that's when you had the maximum torque because it wanted to rotate. That mu wanted to rotate towards that B. So the answer was D for this one. Let's look at one more question. If released from rest, the current loop will do what? So we have a current loop here, and we're seeing a cross-section through this current loop. So the current loop is horizontal. So it's a horizontal loop. I have that square loop here. It's not circular, but it's horizontal, and you're seeing a slice through that loop. What's it going to do? If the current is going as shown, so the current is going into the page on the left, out of the page on the right, and the external field is to the right, what is that loop going to do? So think about it. Think about, is there going to be any rotation? Which way is the magnetic moment? Which way does that magnetic moment want to line up? Okay, so the first thing to do is to figure out which way is the magnetic moment. If you put your fingers in the direction of the current, it's going to look like this. On the left side, so have your hand right in front of you and look at it just like I'm looking at my hand. The left side here, the fingers are looping into the page, and then they curl around, and then on the right side, my fingers are coming back towards me, right? I can see my fingertips. So when you put your hand down like this, the current is looping clockwise as viewed from the top. And that's exactly what this picture is showing because it's into the page on the left and out of the page on the right. So that means that the magnetic moment is going down. So to go ahead and draw the magnetic moment going straight down. And now we know that the magnetic moment wants to line up with the magnetic field. So magnetic moment is going down. It wants to rotate all the way to the right. I can't rotate all the way, but it wants to rotate this way, all the way to the right. So that's going to be a counterclockwise rotation. So there is a lot of visualization in this chapter. Please practice, lots of practice questions to practice these right-hand rules. I will see you in the next video.